Good morning, everyone. How are we all doing? Looks like the sun is just starting to come out here in Sydney. It's been raining all morning otherwise. A lot of questions in chat at the moment about challenge exercises. I was talking to people a little earlier and I thought that we were talking about just the random challenges that I throw out in the lectures. People are also talking about whether or not and how to do the challenge exercises in the tutorials and the labs. There's something that you can do if you're interested, or if you've got some spare time, or you want to kind of dig deeper into something. As with all of the tutorial and lab content, you don't actually have to do it in advance. One of the ways you can learn a lot from these things is to do them in the lab time. For a lot of them, it should be possible to do at least the standard lab stuff should all be able to happen during lab time. Challenge exercises, plenty of them probably can't be finished in the 2-hour time, so that's kind of if you think you have extra time to work on things. Once we get deeper into term, I'm going to assume that a lot of people will potentially not do as much of the challenges in the labs because we've actually given you things like assignments to work on. So if you're looking for more work to do, you're looking for other ways to kind of test yourself with programming, we should have plenty more content for you to do that if you want to. So it depends whether you're looking for cementing the ideas that we've taught you, in which case you kind of do want to do more questions at the same level, or whether you want to try to see some deeper ideas or the ramifications that follow on from individual bits of things we've learnt, in which case stuff like the challenges in the labs are interesting things to do. As the weeks go on, we're going to start releasing revision questions as well that you can do, so once we've gone past a topic, you can go back to it if you want to, and you can test yourself out on things. Those are pretty good because most of those that we're going to release are exam questions in one way or another, or in that kind of format, so people thinking about that kind of thing can get into those. But we'll get into that when it happens. Okay, so let's have a look at today's. First up, what did we look at last week? So last week we had our introduction to COMP1511 because we're in the second week now, so it was, the very beginning. And so we looked at what COMP1511 is as a subject, and I think some of the important things I think from the first lecture is if you're not sure where you're up to in the course at any point, or you need help and things, going through that first lecture gives you a lot of information about where to get help and things like that. And there's an intro video that's linked in that first lecture, and it's also the intro videos with all the lecture recordings, whether it's on the YouTube playlist or in the Moodle playlist. It's there as well if you need it. If you don't really need to know that information in a video format, there's also the course outline, which is published on the course website. We introduced C as a programming language as well. So we looked at the basic setup of a C program, and then we started to learn some of the, I guess you'd call it, C programming constructs that we can use to start building up programs. So printf and scanf allowed us to communicate with a user via the terminal. And so we're starting to get used to using the terminal. I threw in a lot of Linux commands in there as well to get you your kind of first look at basic navigation of things in a Linux terminal. And then we looked at a lot of little things that we can do. So we can have variables, and if I want to sort of remind you of one of the things that we're thinking about, the fundamental idea of what a computer is, when we think about what a computer can do for us as a tool, it has, when it boils down to it, two parts. One which remembers stuff, and one which does stuff. And I want to keep it like, as simple as that, because fundamentally, when it comes down to it, that's all a computer does. It either saves information or it calculates something using that information. So basically, a computer has some kind of mathematical component and something that stores zeros and ones. And then everything that we pile on top of that on a computer is just more complication on that basic idea. So variables are our first way we think of how to store things. And then things like maths operators, or relational operators, and logical operators, all those kinds of things are ways we decide what we're going to do with them. Maths is the most basic element of just calculation. But then relational logic operators are used with if and else statements to be able to decide how we're going to do our calculations, or on what we're doing our calculations. Just looking at chat. Chat's going pretty fast at the moment. I think Tom is answering a couple of questions there, which is good. Someone was asking about Chicken. Chicken's not here right now. She's in another room somewhere, but she might come back later. Okay, so what are we doing today? I'm not necessarily introducing anything super new today in terms of more programming constructs. I think me throwing about 5 or 6 different kind of things at you on Friday was enough, but we are going to go deeper on all of them. So we're going to do a quick recap of some of the things we looked at last week, just to make sure that they are fresh in everyone's memory. And then we're going to start thinking about the process for problem solving, and I'm going to take you through the dice checker again, but I'm actually going to ask some questions that people are asking. Did I just say ask them? I'm going to answer some questions people were asking on Friday about, okay, what if this, what if this, what if this? And so we're going to take one of those, and we're going to go deep on this and say, all right, if we have something like this in our code or in the program we're making, how do we pull it apart? How do we look at conceptually solving the problems that we have? And so I'll get deeper into it once we actually get to the slides. But the idea that we're getting towards here is that solving problems is a very, very generic human skill. We're going to look at it in the context of computer programming, but I think that what I like to think is like a lot of things that I'm going to teach you hopefully will bleed out into other parts of your lives and things. And so the ability to break down a problem into its parts and decide between possible solutions is something that's very, very fundamental to engineering itself. And when it comes down to it, you know, like when I open out, so we're talking about programming. And we're talking about program not just as making programs work on a computer, but we're talking about things in terms of what is computer science. And that's a bigger thing than just programming, right? It's about thinking about solving problems with computers. And then we think about the wider perspective of that. Computer science is part of this kind of human field, which is engineering. And engineering is the idea that an engineer can just sort of... this is a simplified example, but can look out into the world and see a problem and say, that's a problem for humans. What can we create to make that problem easier for humans? Or what can we create to make that problem go away in some ways or another? So when we're thinking about at a low level in programming how to solve problems, what we're actually learning about is actually quite a larger idea that if you want to go into computer science as a kind of a full-time career or something like that, you will end up running against this kind of thing all the time, where you find big problems and you say, how do we break a big problem down into its smaller parts and try to solve it? We're going to go deeper into this as we go through the course. In fact, if you are doing a degree that involves computing, you're going to see this over and over and over again. The idea that we will always get thrown up against things that seem too big when we first see them. But learning how to tackle things that are that big, or how to transform a problem into other problems to solve them is pretty cool. We're not going to do all of that today. Obviously, we only got 2 hours. We're going to look at one kind of way of dealing with problems, and then hopefully that gives you some food for thought for later. Okay, quick recaps. Oh, okay. Someone has come to say hi. There you go. Someone came across to get herself a warm lap. So that's what people were hoping for. So, recap of last week. First thing, in terms of technical programming stuff that we were looking at, was variables. So this is our way of storing information in memory, and all the information that we store on our computer is going to be made up of bits which are either 0 or 1. They're usually collected together into bytes, which are sets of 8 bits. And when we make a variable, it will usually be using a specific amount of memory. So for the moment, and especially like this is thinking about our computers and VLab, our integers are going to be 32 bits of information, and our doubles are going to be 64 bits of information. When we create a variable, we're also usually creating a variable for a specific purpose. So we're going to try to choose the name to make it meaningful. The rules I use for choosing variable names are usually two things. One is something that explains what it does, explains its reason for existence. And the second thing is, does it not just explain its reason for existence, but differentiate it from the other variables in the program so it can't be confused with other things. And if I can follow those two rules, usually I think, yeah, that variable name is good enough. And they're called variables because they can change, which means we can change the value as we go. So the equals sign that we were using to put a value into a variable, we can use that anytime we want in our running code to change the value that a variable has. We also looked at reading and writing to terminal using printf and scanf. If you want to go back and look at the exact format of how they work and stuff, go back to the previous lecture, have a look at... I went into a reasonable amount of detail about how we can put variables into our printfs and how we can read specific variables using scanf as well. We looked at the maths operators. These are working in a way which we expect them to with the plus, minus, multiplies, and divide. We can use brackets as well to force order of operations one way or the other. There's also modulus, which I mentioned briefly, which because if we're doing division with something like integers, we're only going to get an integer response. It's always going to drop the remainder. Modulus is a way we can get the remainder of a division instead of doing the division itself. Modulus is a weird one because I think it doesn't come up that often in maths, but we actually tend to use it a fair bit in computer science. It's kind of useful for a lot of the kind of whole number arithmetic that we're going to be doing. So I can't remember if we're going to use a bit of that today or Friday. We'll be looking at modulus again. I think it's Friday. I keep getting confused because I prepare the lectures in pairs and I think, okay, which one's the first one, which one's the second one? Okay, so relational operators. These were very strongly connected to the idea of the if statement, which was asking a question. The relational operators are the kinds of questions we can ask where we can put two things, one on either side of one of these symbols, and that would be numbers or variables, and they will allow us to determine the difference between them, in a sense. So if I have something like a greater than symbol here, and I have a number on the left and a number on the right, if the one on the left is greater than the one on the right, then the whole thing will end up basically, when you run the program, it will end up sort of transforming itself into a number 1. And we think of the number 1 as something we'll use for true and the number 0 for false. When it comes down to it with the if statement will actually accept any number for true and 0 for false. So there's other things that we can do with those as well. The subtlety of doing that with if statements we'll get into later. But yeah, lots of different questions we can make. And for the moment, those questions are just based on numbers. As we get deeper into the course, we will learn that there's plenty of things that can result in a 0 or 1. We can make our own custom things that result in a 0 or 1, so we'll use lots of those different things in our if statements by the end of the course. Logical operators and or a not are things that we're going to use to join multiple questions together. So the idea that we need two conditions to both be true for us to go ahead with an if statement, we can do with an and, or the or says I only need one of two conditions to be true and I'll go ahead. The not is about flipping these ones and zeros to their opposites. We also looked at if and else statements. So I think this is kind of where we got to by the end of Friday's lecture. And I've got an interesting thing here for you, a little gift. One of the challenges, not the lab challenges, just the random things that I came up with to throw in the lecture to see if you were interested in doing was, what if we had the idea of beating a number as one possibility, so anything higher than it, or matching the number exactly as one possibility, or not matching the number, so being lower than the number. This is when we roll dice and checked against the target. So this is actually something that I would do as a series of if statements to decide the control of the program between these three possibilities. So you can see I've asked a question, is it higher than the target? If so, we say this. If it's equal to the target, remember, if we're asking a question about equals, we're using two equal signs, not a single equal sign. So a single equal sign is a command. It's an assignment, we call it, where you assign a value to a variable. Whereas the double equals is the question, saying, are these the same? Dear computer, could you please look at these two values and tell me whether they're the same or not? And so we can do that there and say, is the skill roll tied? And the else is all other possibilities. If I'm doing this if, else, if chain, the else's only get hit if the question above them in the preceding if statement turns out to be false. So if I go if this, if not this, then this, if not this, then this, means that only one of these three possible bodies of code will run. So it's either we succeed or we tie or we fail, and we're never going to get more than one of these messages at a time, and we're always going to get at least one of these messages because we put this else at the end that says no matter what else, if we didn't meet these other criteria, we will always run this last one. So this is a really, really common sort of programming construct like this, to say there's one of many possible paths that we could take, and we will take exactly one of these paths using this if, else. And you can put plenty more of these else ifs in between if you want to. I'm going to move my face so that you can see the meme. This one's not quite a meme, it's just something kind of funny. I see a question there. I'm wondering if I should go back to it. Someone asked, why is there no if next to the second else statements, but there is for the first one? So else doesn't need an if afterwards. We have an else if here saying, else means we go here if this fails. If this fails, we go to this else. And then we say, but we're not necessarily going into this thing. We're only going into this thing if this happens. And this says we go into this if this one fails. So we hit this else if both of these conditions fail, in a sense. So both of these conditions are false, then we hit this else. And if either one of these conditions is true, then the else gets skipped and it doesn't get run. So the trick is the if else's are nearly in pairs, in a sense. So this else if is paired with this else, which means only one of these two will run. And basically from this else, it starts a new chain of an if else. So this, if you wanted to, I guess you could put the if on another line, but we tend to always do it in this format where the else, the if follows directly after the else. I don't know if that entirely answers your question there or not. Also, I was pointing at things that I was covering up with my face. But anyway, let's move on to the next slide. Okay. So, very cat themed today because Chicken's already visited us. I thought this was quite funny. The cat is stuck and can't find a way out because it's focusing on one particular way around things. So I want to talk about problem solving. I want to talk about problems and talk about making different solutions to our problems and ways we might think about different solutions to our problems. I'm going to propose a problem today with the dice checker that we made last week and look at ways that we can potentially solve that problem. Sorry. Just fixing up my camera because I moved it to show you Chicken earlier. Okay. So the question that I'm asking is, what is our problem? And there's always a good question. One of the things that we can do when we get caught up in programming, and this is a really, really common programmer thing. I think it's common for anyone that gets sort of fixated on doing anything. But programs get you and programming gets you kind of thinking very abstractly a lot of the time. You can think really, really deeply about one particular thing, and you sort of your brain goes down a rabbit hole, and you end up in a situation where you're so focused on getting the nitty-gritty done in a piece of code that you forget why it existed, and you forget what you were trying to solve with it. And sometimes that leads us astray off on a different path, and we don't end up solving the original problem. So it's always quite good to say to yourself, what is the problem that I was trying to solve? And you get partway through and you think, oh, how does this relate back to my original problem? And so I think that's kind of handy. Keeps us on track in a sense. And if we haven't even started coding yet, it's also very good to think about things. What we find, the deeper we get into programming, it's kind of funny. The deeper we get into programming, the less coding that we do. So the less time we spend typing code in our computer, and the more time we spend really thinking about what it should be. And it gets to the point where there are people who are, seasoned professional computer scientists and engineers who just don't do code. And there's absolutely no need for them to do code, because sometimes the much more difficult questions to do with computer programming are, how are we going to approach the solution to this problem? And you get this kind of thing when you realize that so much of computer programming is based on mathematical algorithms or mathematical proofs that solve certain problems. The mathematician doesn't need to know any computer programming at all to be vital to the computing industry. And so we get that kind of feeling sometimes where we will spend more and more time on something like a whiteboard than we will at our computer. I did a lot of that in the past, where it was all just like, theoretically, because we understand what our computers are likely to do, how do we solve our problems that way? And like really just drawing pictures about things rather than writing code. And then you do the code afterwards, after you've spent, like a few weeks or months just toying with ideas and trying to make them work or not. So, coming back to Earth and to what you're focusing on right now, the thing I'm trying to say is, if we keep in mind exactly what we're trying to solve, we can keep focused on many different ways to solve that problem. So we keep writing code and saying, okay, how is this helping us solve the problem? Then we write different code and say, how is this helping us solve the problem? And we're going to do a bit of that today, actually. So, here is a kind of a process that we can apply in general to solve problems. And these won't necessarily be always computer science problems that we'll solve with this process. This might be something we'd use to solve a bunch of other problems as well. It's usually pretty good for a situation where something's not quite right in what we're doing, and we want to figure out how it's working or not working and where we want to go with it. So first step is figure out what's wrong. This is harder than it sounds, because sometimes all that you have for what's wrong is some kind of evidence that something is weird, or you can only see the consequences of a failure, not the cause of a failure. So that's why we're going into problem solving, because we don't really know what's going on. So we want to figure out what's wrong, or we say we haven't made anything yet, but we know that something's wrong in the world and we want to solve it. So we go, okay, we need to think about that. We need to say, okay, exactly what is this? And then we go, okay, what are our options? The nice thing about learning about this in computer programming is when we're doing something like a C program, we have a really specific set of things we can do. So if I'm talking about your C programs now, I could say, this is it. Like, this list here is pretty much everything that we've learnt so far that we can do things with. So it's pretty easy, because it's like each one of these has a function that it can perform, and it will do specific things. And so if we're thinking only with these 1, 2, 3, 4, 5, 6 different categories of things we can do with programs, it's easier for us to look at a problem and say, okay, what things do we need to solve this problem? Potentially it's going to be like, we need to to work with a pair of numbers. So we always know we're going to need some variables to store those numbers. We're going to need some relational operators to check those numbers against things, things like that. So you start to think about, given the problem, what things can you do? And so now it's simple. We only have a few things we can do, but it pretty quickly, once you learn a bit more about program, gets to kind of an infinite realm of possibilities. And then you'll get to see this as it goes on, that when we're working in labs and stuff, we're often sharing code between students. So we're often going to encourage you to work with other people on things like the lab exercises. You'll get to see that one of the funny things is many different people working on the same problem are going to have completely wildly different code, and they're still going to solve the same problem, but they're going to solve it in very, very different ways. And that comes from the fact that we have a lot of options. So we can think about what code we could write, or we can think about, if we've already got code, how are we going to change things? Where should we insert new code? At what point makes sense for us to sort of interrupt where the code was flowing before? We're going to do all this in an example later as well. So we try an option and we say, how well does that option solve the problem? So we go back to the first problem again. We can say, okay, we have identified what's wrong, and we want to figure out how well our new idea solves the problem. So we've figured out what our options are, and we've said, okay, let's try some of those. And then we say, okay, let's try to apply something and see if it works. And then we attach that in some way to our code. We insert it into our code by editing our code, and then we see if it works. When I say, does it work, that's also an entire field within computer science. People have spent decades working on the idea of, how do we actually tell whether that code worked or not? So we could do something really simple, like saying, for your lab exercises or something, does it pass all the auto tests? And it's like, yeah, it could pass all the auto tests, but does that mean it actually performs the task that we asked you to do? Does it actually answer the question? And the answer to that is not necessarily. So this is the funniest thing that I think about programming with auto tests in something like COMP1511, is if you want to, you can have a program that says, that looks at the auto test input and looks at the output the auto test is expecting, and you just say, if the input is exactly this, the output is exactly this. And then you go, all right, that was the first auto test, I've now passed it. Look at the second auto test and go, oh, else if the input looks exactly like this, the output should look like this, and so on. And then you'll just go through the set of auto tests we've given you, and then you could potentially pass all of the auto tests with a program that does not perform the functions that we asked you to put together in the lab exercise, and you will pass all the auto tests. So that's interesting. You'll be able to get something that passes all the auto tests. You'll immediately fail all the marking tests that happen in the background, because they're not the same as the auto tests, but they are checking whether your program does what we asked you to do with it. So we can have options that solve our problem in a certain way because of how we're testing it. So we'll need to think about that when we build solutions. I'm never going to bother building a solution in front of you that just isn't an if-else based on auto tests or something like that. But it's good to think that sometimes our testing and our way of verifying whether something's working or not might send us in a certain direction, and it might not be where we actually needed to be. So if something does work, if something doesn't work, either way, we're going to get some more information, and we're going to see, okay, so if it didn't work, that's fine. We've got some information. We explored an avenue, and maybe the only information we got is like, don't try that. That doesn't solve the problem. We go back here and we look at our other options. We try something else. Even if it does work, it might not be the solution to the problem that we actually want to use. So we might hit a point where we go, okay, this technically solves the problem, but then it's kind of not giving us the kind of solution that we think is best for the situation. So we may still go back and try something else. So there's lots of different things that we're going to come to with this idea of problem solving. And I think that what we need to do is bring this into a more concrete example, and since I only have one concrete example to work with you, I think this will still be interesting. So we're going to use the code we wrote last week, and if you haven't seen it, it's okay. I have it in the code folder, so I think everyone has probably seen the link to the code. If you haven't seen the link to the code, it's on WebCMS. You should probably check that out. There's a link to today's code. If you just have a link to the web page that I had all the code in, actually let's go there. So I think this should work now. So if you go web.cse.unsw.edu.au, I don't know how small that is there. Should be, there should be 4 lectures here, and we're in lecture 3, and there's Dice Checker Starter. So I've put some code in there, which is what we finished on Friday, which is what we're going to start with this week. Hopefully people could see that web address. If people can't see the web address, but someone knows it, can someone throw it in chat? Actually, why don't I do that? It's like asking other people to do stuff. All right. Here we go. I'm going to copy that, throw it in chat for you. Okay, back to my slides. So let's talk about the situation we have here. So, Dice Checker. It was a program that asked the user to input the value of 2 dice they were rolling, and it reported back whether that total was above or below a target value. I think it was equal to or above was one option, and below was the other. But as you can see, I also have some code here for greater than, equal to, or less than. And I think another challenge was like, can you detect when both dice are the same? Little things like that. So one of the questions that came up, we're not going to go super deep into what happens when scanf doesn't work, because we're not ready to unpack when scanf doesn't work. There are pieces of knowledge that I want to take us through before we can get into that. But what we can do is we can assume that the user is entering numbers. So I don't know if anyone's tried this, but you try entering letters or words in when scanf is asking for a number, and things go very weird. I'm not ready to explain that yet. We need to learn more before I can explain that, but I will eventually. But for the moment, if we assume that the input is numbers and can be used as numbers, what happens if they're incorrect values? So we've got a whole bunch of dice here, right? And each die type is specific in that its lowest number is 1, but its highest number might be something else. There's a 4-sided die here, 6-sided, which is the ones we've been using. These are the most standard dice, but you've also got 8-sided dice, 10-sided dice, 12, 20, right? So there are a lot of different dice sizes, but either way, there is a possibility for someone to type in something that will be happily recognized as an integer by our computer, but will be outside the range of what values these dice can have. So what we can do here, so this is the input code that we have already. So we've got the 2 die variables. Hopefully I named these the same in the code. I'm pretty sure I did. And then we had this code that was going to say, please enter a number, and then scan in their input like so. And then we have the same 2 lines, not exactly the same, but very close to the same 2 lines here for the other variable. So this code here should ask our user to type something in. When our user types in a number, the number value that the user typed in will get put into this variable, and the variable was already made and ready to accept values there. And then we'll do the same for the other variable. So by the end of this, the numbers that we type in should be memorized by our computer in these 2 variables. Let's look at the problem then. So if we're assuming we're still just using the 6-sided dice, I'm going to show you how we can do this with different sizes as well. But assuming that we're just working still with the 6-sided dice, we have the values 1, 2, 3, 4, 5, 6. Those are the only values that we're happy using. Any values outside of that range are things that we would consider invalid die values. So things that shouldn't be possible on a 6-sided die. So what we're looking at is accepting inputs within this range here. So I've got a number line here. It's totally not to scale. If it was to scale, I think the 1 to 6 would be this tiny, tiny pixel next to the 0, because there's billions in either direction here that are all valid integers, right? So now we have this situation where it's like, okay, if we have this massively wide input range, how do we detect whether a number that was given to us is correctly within the range, or it's outside the range that we're supposed to look at? So we've got some code here. I think it's probably better that I don't go through this slide, but we type this code in and have a quick look at it, because there is an if-else statement happening here, which we're going to hop across to our code. Oh, don't worry about all this. I was just navigating through my directories here. I had the funny thing. I was talking about getting confused before between which lecture is next, because I set up lecture 3 and 4, and I went to 4 by accident. So, if you want to, you can look at my Linux commands here. So I went to my public HTML directory, which on your end, you will see anything I put in my public HTML when you go to this web address here. And so in here, I went to lecture 3, and I have the dice checker starter code here. I'm probably going to leave the starter code in its current state, which means what I would like to do is make a copy of this code and start editing it. So in order to make a copy of this file, I'm going to do cp, and I'm going to start typing it and press tab. When I press tab, it's going to try to autocomplete. Basically, the more organized you are with your files, the easier it is for autocomplete to do things. Because I only have one file in that directory, pressing tab is going to autocomplete this. So I have copy this file, and I want to make a new file that I'm going to extend the dice checker with. I'm going to call it dice checker 2, because it's going to be the second version of the dice checker. I know it's a C file, so I'm going to do .c on the end. So this is going to copy this into this and make a new file there. The terminal has not told me anything, and usually if the terminal doesn't tell you anything, it means it's completed things successfully. But I'm going to check with ls, and I can see now I have dice checker 2 and dice checker starter. So the dice checker starter is something for you, so that you'll always have the starter file, but the dice checker 2 is the one that we're going to work in. So I will now open my editor using the command gedit. Dice checker, I'm going to tab complete this. I can get this far. I'll type the 2 in to decide between the two files. Actually, one thing that you can do with autocomplete, if you press tab multiple times, it's actually, you only need twice. I press it 3 times there. It'll show you a list of all the files that match the partial file name that you've typed in so far. So you can see that and be able to decide between files. So dice checker 2 is the one that I want, and allows me to run both my editor and my terminal at the same time. So here we have, just going to get that out of the way of my face there. Probably going to need to bring this over here a little. Right, here we have the exact code that we wrote on Friday. Nothing new yet, but it has, asking someone to type in a value of a die, asking someone to now type in the value of the second die, scanf, reads whatever value the user types in, stores it in the variable. So this is our storage of those variables. And then we're going to print out the values that we read in, print out the total, and then print out whether they were succeeded or failed based on this if-else statement here. So now I have the situation where I want to figure out whether the roll was valid or not. So I'm going to do this separately for each of the 2 dice. When we get further into the course, I'll show you a way you can do this where you only have to do it kind of only have to do it for one of them, and it'll be able to do it for both of them, but not yet. Not too much complexity all at once. So, I want to decide whether this input was correct or not. If I want to do that, I need to ask a question. So a lot of the time it's like, okay, I'm gonna do the format first. I think I said this last time. I'm gonna do the format first, and then I'm gonna fill it out with the information that I need. So, I have two possible conditions. Either it is in the range that I want it to be in, or it is not in the range that I want it to be in. So let's ask, is it in the range? So the range is from 1 to 6. So I'm going to say, is die 1 greater than or equal to 1? That cuts out 0 and all the negative numbers. I also need to cut out all the numbers higher than 6. So I need to say it's greater than or equal to 1, and it's also less than or equal to 6. This allows me to say that if the die is within the range 1 through to 6 inclusive, then it is a correct die roll. I had a question last week, which I should probably look at. So if I didn't do it this way, and I tried to do this, this makes perfect sense mathematically. We would definitely write it like this mathematically. So die 1 is greater than or equal to 1, and it's also less than or equal to 6. Unfortunately, C is not okay with this. Its relational operators like exactly one thing to be on either side. So I want to check something. I don't usually write code like this because I already know which way it likes to work. I want to see if this actually compiles. So let's run our compilation. DCC dice checker 2, and I want it to write an output file called, I'll call it the same name as the C file for the moment. I think that's identifying our program fine. Dice checker 2. I want to see if this actually compiles, because I have a feeling that it will actually consider that to be legal C, but it may not give us the answers that we want. Yep. Interesting thing, there are two ways that your compiler can tell you stuff. DCC will tell you stuff. One is an error. When it gives you an error, it says, I will not compile this program, it cannot run. So that's what happens if it can't understand the code that you're writing and can't make it work. A warning is something that says, your code technically runs, but I think that there might be a problem with it. You might have an issue here. So I think what's happening here is result of comparison of constant 6 with Boolean expression is always true. So our relational operators, 1 less than or equal to 1, are what DCC is calling a Boolean expression. A Boolean expression is something that always has a 0 or 1 as a result. So the interesting thing here is it's saying, I'll do this one first, and I'll get a 0 or 1 result out of saying is 1 less than die 1. And it's like this. It's like this is what it's done. It's is 1 less than or equal to die 1. So let's say die 1 happens to be a 3 here. If 1 was less than or equal to die 1, then this would transform into 1. It would transform into true, and then we'd be asking, is 1 less than or equal to 6? Then this if statement will always run. The only other option for this thing is if it's a 0, if that was not true, that's also less than or equal to 6, which means this question is not asking what we want it to do if we were to frame it like this. So it's not capable of dealing with this multiple questions chained together, which is why instead we say we have separate conditions and those are logically connected in some way. So I can do it like this. 1 less than or equal to die 1, and die 1 less than or equal to 6, we have valid input. So I can say die 1 is between 1 and 6. And what I might say for my else statement here is die 1 is outside of 1 to 6. I often like to write stuff in my else statements because if this code is long enough, let's say I wrote a whole bunch of stuff in that, and I'm coding in my program and I look here, I might forget what the if statement was. Once it's off the screen, it's hard to read, it's hard to remember, because I might have this much code in here, there. So sometimes I like to have this to just remind me, okay, this was what was happening here. And I might even give more information. This is valid. And this is invalid. Okay, I'm gonna save, oh, should probably save it without all the unnecessary white space that I put in there. Yeah. Okay. So what we have now is a way to branch our code. This is exactly what if-else statements are for. Is a way for us to decide we're going to do this thing or we're going to do something else. So we're either going to do one thing or the other. So I'm going to say that there's one behavior I'm going to do if the input was valid. There's another behavior I'm going to do if the input was invalid. So this way I can potentially do things like say I am not going to do the thing you asked me to do if the input was invalid. I'm not just going to blindly add these things together and let you pass this dice check if you type in, whatchamacallit, like if you just type in 99 or something as one of your dice, and I'm just like, okay, no, you're cheating, we're going to stop that, right? So this is our way of testing that kind of thing. So with this, we have now added, so previously with the if statements, we were just testing two values against each other. Now we're testing a value against one number, and, sorry, it's a variable against a value, and the same variable against another value, and saying, I need both of these things to work. So if both of these things definitely work, then I can do something. If either one of these is false, so if it's above 6 or it's below 1, then we go down in here and we say that was outside the range that we thought was good, and it's invalid. Okay. Another thing that we can do, move this out of the way. I did say a second ago that we can have different sizes of dice. So let's try using constants for these. So if I have the values 1 and 6 in my code, that means that my code can only ever be used for a 6-sided die. But I said there's all these other sized dice. So let's now set our program up to be able to use a minimum value and a maximum value on our dice. And this way we will always be able to know what our minimum and maximum values are. It also means that we're not going to get confused in our program about when we're using the size of the dice, because they will be in these big bold text that this is the min value and max value of the dice, and so it's really easy to read. But the other thing that we can do now is it'll be really, really simple for us to change between the size of the dice, because all we'll do is change the maximum value, and we don't have to look in our code or change anything else in our code. This is basically going to go through and find anywhere where we're referring to the size of the dice and change it for us. So this is one of the powers of using constants instead of doing things like writing these numbers in here. So if I use constants and I wanted to do something with the other die, then I wouldn't have to go through, if I wanted to change it between a 6-sided die and an 8-sided die, I'd have to change it here. I'd have to change it somewhere where I was processing the second die. And I'm not sure if there's going to be somewhere else in here that I'm going to use the size of the dice. So it's really neat to do this stuff in these hash-defined constants, because it means that going to the amount of trouble it takes to change the size of the die will be changing one character in our code, as opposed to if there's 6s strewn through my code somewhere and I have to go through and find them all and change them. And it gets even more confusing if there are 6s in my code that aren't related to the size of the die, that I use the number 6 for something else later, then that's even more dangerous, because I won't know which 6s to change and which not to. So putting in a hash define makes it really, really kind of nice like that. Okay, so I've got the min value there and the max value there, And I probably don't want these to be 1 and 6. Okay. Now it's nearly getting to the point where I can give this line of code to someone who has never done any programming and doesn't understand programming, and they actually have a decent chance at understanding this. So this is how we increase the readability of what we're doing. So they will read this in English and go, if min value is less than or equal to, they're potentially going to understand this if they just read the names of the characters out. If min value is less than or equal to die 1, and die 1 is less than or equal to the maximum value, then it is valid, right? So we can nearly get to the point where our code is written in such a way that we can understand it without knowing C. And that's like this kind of holy grail of programming. If you can get your code to the point where someone who doesn't know programming has a decent idea of what happens in it, then you know it's actually very, very well explained. So not only are we saving ourselves the hassle, if I want to change this to like a 20-sided die, that's all I have to do. I'm also making this much more understandable in terms of just looking at it and seeing what's happening. Okay, so the constants are going to help us like that. Yeah, this is a good time for a break. It's a little early, but we're going to do more in the second half. So, we're going to take a break now for 5 minutes. I have some trivia here, in case anyone's interested. Just looking at dice and the fun stuff that dice and randomization have added to human games over the years. So, as far back as we can see, based on historical record, the Egyptians were using flat sticks that could land on one side or the other, like the same way we'd toss a coin, to randomize movement in a game called Senet, which is one of the, I guess you could consider it, precursors to all of the board games that we play now, and that puts it past 3000 BC. So we've been using dice for, let's say 5,000 years at least. And six-sided dice have been found in Iran, dating to 2,800 to 2,500 BC. So those six-sided dice, I've put them away, but I'll get them back out later, have been around for ages. And we're using, as I said, 4 to 20-sided dice. And there's also the idea, and people were asking me about this, of using random number generators in our code. That uses libraries, which we'll talk about later in the course. But when we talk about libraries, if I remember, I will show you the random number generator as well. It's not too hard to use. If you want to look it up yourself, you can. But don't worry if you don't yet, because we'll get there bit by bit. I try to make sure that what I teach you is really specifically in an order of how we're going to use it, not necessarily jumping around between things. Okay, so we're going to break now. It is 11:52. We will come back at 11:57. According to my clock there, it's about 5 minutes time, and we'll continue. We're going to do more code. We're going to look at multiple different ways we can approach the issue or the problem that we have of the user potentially being able to type in a number that's not in the range we're looking at. Okay, see you soon. Alright, we're back. So, continuing, let us now think about what our problem is and what we're going to do about it. So, first thing that we do is we have a well-defined problem here. So we have figured out the integers are a very, very, very wide range of possible numbers, and we only want a certain very small set of those numbers, so between our minimum and maximum value, to be something we actually use as a dice, and we need to know what we're going to do if things are outside of those values. When they're inside of those values, it's fine. We've already got something we're going to do, because that was our program last week, which was just deal with the input, add them together, check them against the target, that kind of thing. So we have several options that we can do here that might treat the invalid input in different ways. So the first one is panic. This, I guess, it's not really an option, but it's the idea that we're not going to do anything about it. So either we're going to just let it go and let it happen, or maybe we could, I was about to say maybe we could end the program entirely, but we actually, this is an option. This is us actually doing something about it. So what we could do is we could say, if the user inputs incorrect input, we just say, nah, hands up, walking away, dropping the mic, I'm out of here, and just end the program. We'll actually implement all of these to show you the difference between them. So we could do that if we want to. And we could say, if you're going to give me values that aren't the dice that I said that you're allowed to roll, I am simply going to not function as a program. There are other things we can do, though. So we could look at the human element to this. So this is us going back to our original goal. The original goal is we wanted a program that was allowing humans to type in the numbers that they rolled on dice, and for us to then say, did you or did you not meet a secret target number that only the program knows, that the user doesn't necessarily know. And so we could actually let the user know, okay, I'm built for certain dice sizes. Maybe you should use those dice sizes. Or we can do other things where we can actually correct the input. So we can say, given the input that you gave me, it is incorrect, but I could still make this into correct input in some way and make it work. Another thing we could potentially do is ask for new input instead. That's a cool one. We're not ready for that yet. We don't yet have the coding constructs to ask for new input. So this one's here in the list because it might be useful, but we're going to look at the other ones first and see how that works. So, the option of rejecting the input. I'm not going to talk about the code on the slide. I'm going to talk about the code in the code editor here. So, if we have invalid input, this is valid input here, we can do something. If we have invalid input here, we could do something else. So at this point, I might think, I've actually got the code here that says this is what I want to do if the input is valid. So if the input is valid, I want to continue my program as per normal. If the input is invalid, I want something else to happen. So looking at this if-else statement, I think I might want to flip this around. So instead of asking the question, is the input valid, in which case I would copy and paste all this code inside this if statement, I might be able to make it neater for myself and say, if the input's invalid, do something. Otherwise, just keep going as you were. So I could do something along the lines of flipping these around. So if the min value, I'm going to ask a completely different question. I mean, it's the same question, but it's just the inversion of the same question. So if I say that die1 is less than the min value, or, so this, I'm using an or instead of an and, or the max value is less than die1. Actually, it doesn't particularly matter what order I do this in, but I might write it this way because it's a little bit easier to read. Or if die1 is greater than the max value, then instead of that now being valid, I'm actually now asking the question of if it is invalid. So die 1 is outside of min value to max value and is now invalid. So now I can say, okay, if something's invalid, I want to do something about it, and then I'm going to let my program keep going. So this allows us to say that even if it is invalid, we're probably still going to keep going, but there's other things that we can do. So one thing that I can do, see this return 0? Return 0 says this program has finished, and the 0 means 0 errors. It doesn't exactly mean 0 errors. We're not counting errors, but in terms of error codes, usually a 0 means that this thing worked correctly. So what I could do is I could say return something other than 0. So you know how you've seen the idea of the 404, something didn't work correctly? I could use that, but that's 404 is very specific. But I could actually start making my own error code. So I could say the first error code that I have is that the die was outside the range that it should have been in. So I can say return 1 instead of returning 0. We're not actually going to see this. So it doesn't actually tell us here in the terminal whether it returned 1 or 0. But if we were sort of interconnecting our program with other programs, there would be a way to extract that information and find out whether it worked or not. So I could do this. So I could say return 1 if it's outside of the min and max value. And this return, as I said before, this return is going to signify the end of the program. So even though there's code afterwards, this return can actually signify the end of the program here. This is a very abrupt way of doing things, but I'll show you how it works. So let's make sure I saved that. Yes, I saved it. When I'm looking to whether I've saved it or not, I look at the file name, and if I've typed something, there'll be a star next to the file name. I'll press Control S now to save, or you can press this button here to save, and there's no star next to the file name, so I'm pretty sure I've saved it now. So I'm going to compile this. In fact, now the trick I showed you last week, I'm going to use again. I have a compilation command here, and the terminal allows me to go through my previous commands using the up and down arrow keys. So I'm just going to go up and find the same compile command that I used before and use it again. Okay, no errors or warnings, which is a good sign. It means that my code is syntactically correct C. It doesn't mean that it's doing the right thing, it just means that it can run. So let's try running this now. Oops, dice checker 2. So type in the value of the first die. So let's just see this working properly. So let's just type in a 4 and a 5. They add up to 9. Dice check succeeded. We have a check only on the first die. We haven't done any checks on the second die. I'm not going to repeat my code. I'm just going to do one die. So we can try a die 1 that's outside of the values and see what happens there. So let's say the user's getting a little bit cheeky and is trying to cheat and says, if I roll a 99, there's no way that I can fail this thing. Oh, I'm a head out. That's what the program's done. It's just said, no, I'm out. There is nothing happening here. I am just going to abruptly end and not even tell you what happened. So this is our first pass through this process. So we looked at our options and we tried one of them, and we now ask ourselves, did it work? And the funny thing about this is there is no clear answer to did it work. It's like, yeah, it worked. The program executed and it completed its execution. There are no errors in compilation and there are no errors in the execution. But did it work is a very complex question. I know I ask it in a very simple way, but it's very complex because it's like, does this thing achieve the goals that we set out for the program in the first place? does its kind of complete rejection of the user's invalid input make it something that's useful to us? So, you know, problems are more complex than we think. Where are we? So, assessing this, was it a good idea to have the program just end? Now, you'll find it's pretty obvious. This is something that you'll get a hang of the more time we spend together. Is if I ask an open-ended question, like, is it a good idea for this to just happen? Usually it's because the answer is no. Or the answer is like, we need to think about this more before we just accept it, right? So, was it a good idea for the program to reject the incorrect input, and is there a better way to do that? So if I'm running this program, should I maybe give some more information? So actually, I'll go back to the slides because I've got another slide for this. So let's try reporting the failure rather than just saying just disappearing. So you don't necessarily, like, I don't know if anyone's ever been ghosted by someone. This is what it feels like. A program just ghosted us. It's not very nice, right? So we want to here actually say, okay, instead of just disappearing, let's at least report that there's something is wrong before we just head out like that. Okay, so we can do a printf here. So we can at least leave something in the terminal saying die1 is outside of the valid range. Program will exit. I'll put a new line on that. Oh, there's something that you may have noticed if you're using gedit. There's a line here at the end. This line is a suggestion that maybe your lines of code are too long. Once the lines of code are too long, it becomes hard to read, because if you've noticed, I don't know, like, we've seen like half a dozen programs now. If you've done your tutorials and labs, you'll notice that when you're reading code, you tend to read up and down on our code, which means we're really, really focused on the left-hand edge. So the further away we get to the left-hand edge over here, the less likely it is we're going to read all of the text. So this line is usually a reminder that something's getting too long. We'll talk about that more later. I have an entire lecture on how to style your code so that it looks pretty and it's easy to understand. So now we have this, which is going to give us a little bit of information. Let's try running this now. So nice that I can use my up and down arrow keys now to find my previous compilation command. Makes this going back and retesting things pretty quick. So I do that, up arrow key again to find the command to run it. I've gotten into an instinct of like up twice, enter, that's compile, up twice, and then run. So if I'm just doing this continuous loop of compiling and running, you can do it pretty quickly like that. Okay, so we want to again try an invalid value to see if to see what happens when the invalid value happens. So last time I was trying to cheat and I put in 99, and the computer detected that I was cheating. So this time I'm like, I'm going to try to trick the computer. If I put in a 0, it won't know what to do with it. Turns out the program does know what to do with it. It's saying, I typed in the value of the first die, it's saying die1 is outside of the valid range, program will exit. Okay, so we have improved our situation a little, and we improved our situation by trying something out, seeing how it felt in a sense, and it was like, okay, it feels like it works, but it feels like a, you know, just like, this is a real kind of, often in program we talk about the idea of brute force solutions. It felt like a brute force solution, this one, where it just disappeared. And now it's getting a little bit more elegant. So it's coming around and saying, okay, now we know that there's something wrong, and because there was something wrong, the program's going to exit. So we're getting better, but there's other things that we could be doing here. So let's say I've got my 0 and my 99. I'm like, okay, I'm going to keep running this thing, because what if I've forgotten what size the dice are? So I'm just like, okay, I'll just keep putting values in. So what about 9? Is 9 valid? No, it's exiting again. What about 12? Maybe 12 is valid. No, it's exiting again. So we're at the moment a little bit lacking information in terms of helping our user get this thing right. So we're pushing them into a cycle of just keep typing in random numbers hoping that one of them is going to work. So the question is, can we do better? Rather than just saying that it was out of range, let's use what we know of things like min value and max value to give the user information on exactly what they can type in next time they try this to get it right. So this is a long printf and it's going over multiple lines. I'll show you that in a second. And it has 3 numbers in it. One of them is the value that they typed in, and then the other ones are the min and max range that they should be using for this. So with that much information, we should be able to tell the user, okay, this is how this thing should have worked. Let's go into the code and actually change that. So let's say die1 has a number, is outside of the range number to number. So I'm assuming that I've got some numbers here, and then I'm going to actually use those numbers. Here on the end, I could have the first one is the value of die1. The second one is the min value, and the third one is the max value. So I'll put those constants in here. I'm auto-completing there. Where I press enter when it comes up to the name that I want to type in, which is the same as one of the previous things I've typed in earlier. So you can see how this line now is gargantuan. It's gone so far off the end that if I want to read it, I cut off all the rest of the things I'm looking at. So it's a bit awkward. It's not great for reading, because if someone's scanning up and down on this, they might miss the variables that we're using in that. So if I want to do something like a printf over multiple lines, I might do something like this. So after the comma there, I might break this and then use the same indentation rules that I've been using with these brackets. So I'll go 4 spaces in here, and I will close these brackets underneath the line that opened them, in the same way that you can see my if statement here has an open bracket there, and the closed bracket is directly vertically below the if statement opening. It makes it really clear that all of this code is inside the if statement, because all of this code is like indented a little bit further in. With the printf, I can say this stuff is inside, and then the closed bracket is here. So it's the same kind of format. We can recognize the format. Some people go to even greater lengths with this and do stuff like that. Up to you. I would only go single column like this if there are lots of them. And then if there were that many, I might say, you know what, I should probably break this up into multiple printf statements. Because when you think about it, printf is just putting text on the screen. If you don't put a new line on the end, you can just do 2 separate printf statements, and they will go directly after each other on the line. So if I wanted to, I could split this up into multiple printf statements. If I want to get really, really hilariously pedantic about it, I could printf a single letter at a time and just do multiple printf statements. But that's kind of giving up the convenience of using printf. The convenience of using printf is in our code, we can just type out this whole line and it'll be like, yeah, I can deal with that whole line. So I've got my 3 values here. I might actually just leave them on one line rather than being on a separate line each, but you know, it's a matter of choice. You could do that. And then I'm saying I'm going to report what the user typed in, what I say is the minimum value of the die, which at the moment is 1, and the maximum value of the die. And this hopefully will give our user the ability to, when they rerun the program, it's much harder to get it wrong now. So, I mean, like, maybe if they're rolling the wrong die size, then they'll know that something's up. Okay, I'm going to save this, use my up arrow key. Oh, you know what I might do? I'm going to use the tilde to shrink my home directory here so that the so that the prompt is smaller. Okay, go back to the directory I was in, which was lecture 3. Now we can compile. And so now I have compiled this program with the new printf statement that is going to give us a little bit more information. Using my up arrow key to get the command I used to run it. Run that again. Now let's see what happens if I give it another invalid input. So minus 500. I'm so frustrated now. I keep trying to cheat and the program keeps catching me. So I'm just going to give it a massive negative value and see what happens. And the program, of course, because the program is implacable and it knows exactly what's going on, knows that negative 500 is not a valid value on the dice. So it's going to tell me negative 500 is outside of the range 1 to 6. And I'm going to say, oh, okay, 1 to 6. I guess I should, next time I run this, type in values that are 1 to 6. Yeah, just checking what... Oh, people are talking about difference between tabs and spaces. I think most text editors that you can use for code can have a way of setting up so that every time you press tab, it actually fills out the white space with spaces rather than tabs. Like, we're still going to mark stuff if it's tabs, but it's nicer and more cross-platform friendly if there are no tabs anywhere in your code and it's all spaces. Having said that, I still use tabs, but that's because our 1511 setup for gedit has all of our tabs, as you can see here with me highlighting it, automatically makes the tabs break up into spaces. So you will have no tabs anywhere in the code that you receive from me, but it depends on if you're using a different code editor at home, whether you'll get tabs or not. Okay, so we have one possible solution here, which says that we're going to send our user back. We're going to tell them that your input is incorrect, you're going to have to rerun the program, but we've given them all the information that they will need in order to get the correct response. And now you can see how we're evolving our solution. So originally it was just like, I'm out of here. The program totally ghosts the user. So up here, type in the value and it's just like, oh, it just ended. Like, what happened? It just ended. I don't know if anyone's ever, just used a program on your computer and it just literally disappears. And that might be this kind of situation where someone's coded something and they haven't thought too deeply about what might happen when something ends. And it's like when you're playing a game and it crashes or something like that. It's like, oh well, I don't know what happened. But sometimes there'll be more information. So it'll be like, there's this kind of information, or there's this kind of information which we would consider to be something that's actually really kind of functionally useful to a human to be able to see that. So maybe that's better. Again, when I say better, it's only better because we're thinking back to the original problem, and we're thinking in the context of this program is being used by a human, and that human is specifically doing stuff like rolling dice and typing it in. So if the human's rolling dice and typing it in, then we know how it's going to be used. If this was not a dice checker for a human, if this was something that was just going to connect up to other programs, then maybe this printf is completely unnecessary and there's another solution that's going to work better, right? So when we say better is in context with the plan for this program. And it's always going to be like that. Every program is going to have a different reason for existing, and then you will decide how you're going to solve your problems based on that. Okay, so at least up to this point, the idea that we're going to mic drop and walk away and just not deal with the invalid input, we have something that is like nearly what I would consider complete at this point. If our decision is to just reject the input. But what if we were thinking about a different way of doing things? So let's think about the possibility of correcting the input without exiting. So what if we want to say to the user, your input is incorrect. I see that your input is incorrect, but what if I help you make it correct? So our options here, there's two ways that I came up with for us to potentially do this. One is this thing called clamping, and I think, I'm not sure at what level of maths people learn about clamping, but you can definitely do this kind of thing where every number higher than a certain value just gets pushed back into that value, and everything lower gets pushed into that value. Mod is a different way of doing this. I'll show you the mod way, because it's the way I came up with to solve this, which is potentially something that you would never do for anything other than a dice program. But it worked in this case, which is, again, going back to the idea that doing things based on the original idea of the program is something that works well. So let's look at clamping. Clamping can be done pretty simply. I wonder if we have... No. I'm going to go back to the number line and show you. So these are all the inputs that we could get that are valid inputs for an integer, but not valid inputs for our specific input range for the die. So what happens with clamping is anything in this range, so anything that's lower than the 1, just gets pushed and it becomes 1. So anything that's too low, we push it up until it's equal to 1. And anything that's too high, we push it down until it's equal to 6. So that way, what goes into our system afterwards is always between the values of 1 and 6, regardless of what the human has typed in. So, show you the code for this. So here we have, this code was outside of the range. Now, we are not going to just exit. So I'm going to take out the exit code. And I'm not going to throw things away, but I'm going to correct the input now. You know what I should have done? Oh, it's okay. You can go back through it if you want. I was gonna maybe save different versions of this code, but what I might do is I'll just keep going through and we'll have one definitive version at the end with the solution that I like the most. Okay, so correcting input with clamping says that if the input is below the minimum value, then it gets pushed up to the minimum value. And so I could nearly say that as I type it. So I said, if the die value is less than the minimum value, it gets pushed up to the minimum value. And so I'm not going to bother pushing the number by adding stuff to it or anything like that. I'm just going to say, if you are outside the range, I'm going to force you to be inside the range. So that's all I'm going to do. I'm going to say, if you are less than the minimum value, then you will become the minimum value. So it's funny because these two lines look really similar, but they're very, very different. One's a question saying, is the die one less than the minimum value? If it was less than the minimum value there, I'm going to say I want you to replace it with the minimum value. So anything below 1 gets turned into 1. And I could say else if die 1, oops, too many enter keys, is larger than the maximum value, it is also, it's the other side of the outsider range. So here it was like outsider range this way or that way, and here we're looking at the individual parts of it. If it's lower than the minimum value, we push it to the minimum value. And then if it's higher than the maximum value, we say, if you were higher than the maximum value, that's invalid. I'm going to force you to be valid by making you the highest value. And then we can continue on with our program, knowing that so long as this bit of code has run on any invalid value, it should have made them into valid values. So it's a little bit weird, when you think about it. And the way to remember this, because I can see a lot of questions popping up in the chat, is that remember that this is a command. This is not a question about these two things. This is us saying that this question, if it was true that die1 was below the value, make it into that value. So I'm saying make die1 equal to 1 if it was less than 1. I'll show you it running because it might be easier to see when it's running. So I'll compile this again and then I will run it. So now if there's an incorrect value on the first die, it will get pushed to the 1 or the 6 basically. So if it's below 1, so -10, it's going to get changed into a 1. So it's reporting that -10 is outside the range 1 to 6, but it's also not reporting, maybe we need to, reporting that it has been changed. So if I make the second die 4, I'm going to get die 1 is now equal to 1, and die 2 is equal to 4, total value is 5. That happened to fail the dice check. We're not worried about that at the moment, we're worried about correcting these. So it said -10, I'm going to make sure you can see, -10 was too low. Oh, actually, let me go to back to the number line. -10 was too low. It's down here somewhere. We pushed it up until it is within the valid range. So 1 is within the valid range. We kept pushing it, basically. We're not pushing it. We're actually just kind of resetting it. So we're saying, if you're outside the range, you now go into the range. And so you go into the closest point in the range. That's why they call it clamping. It's like pushing all the numbers in to this point. So if you're outside the range, you get pushed back into the range, and now we can use that as if it's a valid number. And we do the same thing if it's higher than the range. So let's try that. So I go my cheaty method. As before, I try to do 99, and it says no, 99 is outside the range. And what if I roll a 5 alongside that? Die 1 is now equal to 6. So what we're getting is that any numbers that I type in that are outside the nice range are now just getting changed to the nice range. So you see I'm using, it's kind of like an extension on all the ideas that we were looking at last week of if and else statements. I'm just kind of adding a little bit of complexity here by using the same variables. So I'm saying if it was less than that, make it that. And if it was higher than this, make it this. So I guess we could have done an if instead of the else if here, knowing that these conditions would never both happen. But I kind of like the else if to say that we're only ever going to do one of these two. So either it's too low or it's too high, and then we just fix it like that. So that's our clamping method. That's us being able to say that if you give me an incorrect value, which I've detected here and reported, I'm going to be able to correct it in some way and say I can make this into a legal value. So this is the same code here, and I can ask, are there any issues with this? So we are definitely ending up with input that works, and that can be fed into the program. But is it correct? I mean, it's not really correct, because if someone types in an outlandishly high or low number, then it just gets set to like 6 or 1. And what we're getting is if someone just starts spamming numbers on their keyboard, it's nearly always going to be a 1 or a 6. And the other numbers are probably not going to come up as often. I mean, if the user is doing things correctly, we're probably never going to see this, but it's slightly weird behavior. The other thing we need to ask ourselves are, what are potential issues of us correcting the data without the user knowing? And this is a big can of worms, because this really, really depends on what kind of system you're using and what it's for. So if we're correcting without the user knowing, let's say we do this in a medical diagnosis program. I'm just like intentionally loading this up. Like if you have a medical diagnosis program and the inputs were incorrect, and you go, oh no, those inputs are incorrect. Don't worry, I'll put them in the normal human range and then do a diagnosis. It'll be like, the reason those values were outside the normal human range was because the patient has a disease we want to help them with, right? We go, no. Human temperature doesn't get that high. We'll just put them back in. They don't have a fever. It's alright, you don't have a fever now. Right. Okay. So, correcting data without the user knowing is a bit of a minefield. And we want to be making sure that we don't necessarily do that unless it still meets the goals that we had for the program, right? So if we have particular goals for how we want something to work, then we do need to make sure that we actually use those. So I want to show you another possible way of doing this, which is with modulus. I'll move my face out of the way of the text there. So a reminder of what modulus is. We were looking at this because when we divide integers, we're going to get an integer result, which means any remainder in a division is simply going to be thrown away in an integer division. That's not really what we have here. We've got a different situation here, but I'll show you what we're doing anyway. Modulus will give us the remainder, which means what we could do is we could turn this dice check program into something that actually acts a little bit like a random number generator. It's not going to be exactly a random number generator, but it'll be a little bit like one. So we can take any number the user types in, and we can mod that number with 6, and that will give us the remainder if that number was divided by 6. The possible remainders when that number is divided by 6 are the numbers 0 through to 5. So if I have the numbers 0 through to 5, that's actually quite nice, because 5 out of those 6 numbers, for one, that's exactly 6 numbers. And if I have 6 sides on my dice, getting exactly 6 different possibilities is pretty good. It's even better that the numbers 1 through to 5 are exactly some of the values that we want. The only one that's out is the 0. We need a 6, not a 0. So if we want to, we can just say, anytime we get a 0, we're going to treat it like a 6. And then we suddenly have the range 1 to 6, and we can get this range 1 to 6 no matter what number the user types in. And we can nearly get to the point where the user can just spam keyboard with digits, and that mod will give us a number. And so it's not a random number generator, but it's a number based on something that the human might not be expecting, because they're just typing random numbers, and we're going to give them something between the range of 1 to 6. So you can nearly treat your keyboard like dice that you're rolling. So let's see how we're going to put this together. So I've got some code here, but what I'm going to do is obviously work on the code rather than just going through the slides with code on them. What I'm going to do here is leave this code in here. But for the moment, I'm going to do something that we'll do often with our code if we don't want part of our code to run, is we're going to comment it out. So I showed you a different way of commenting before. It's okay if you've forgotten it, because I just showed it once in a slide and never used it. So the /* and the // allow us to say this entire section of code that is in between these two symbols will not run. It'll be used as comments. So comments are usually things we do in order to say something to a human, but we can also use the kind of secondary function of the commenting, which is that the computer will not read stuff that's commented. So we can use this here to say, okay, here is one of our solutions. We don't necessarily want to throw the code away because it's interesting to see, especially if I want to give you this code file afterwards. I want you to still see that this was one of our possible solutions here. So I'm going to leave that there like that in a comment. When we're doing lots of comments, like multi-line comments like this, often this is much easier for us to work with than having to do a // at the start of every line. So if I wanted to, I could do something like this. And if I was typing this in from scratch, as opposed to editing it now, this would be much easier. So you can do something like this, right? And that means you're not doing the // on every line. It's kind of nice and easy. And my gedit is not cool with me doing that. it's only the autocomplete thing is trying to keep a library of the words that I've typed in, and because I changed, like, technically changed a bunch of them here, it's throwing these little warnings. Don't worry about them, not a problem. I'm just going to clear that. So I typed in the word clear there. You can do that if you want to. The word reset also works the same way, that will clear up your terminal so you have a fresh window, you can start again with it. Okay, so I've commented out that, and this time I'm going to say correct input using modulus. So let's piece this together, and I'm going to show you bits and pieces of this working as I do it, rather than write all the code and see it happening. So die1, I've already, if I'm inside this if statement, which I still am, if statement ends there, I know that the die1 is outside the range already. So what I'm going to say is die1, I'm going to replace the value in die1 with a different value. So I'm going to say die1 is now equal to something else, and the something else that I'm going to put in there is going to be die1 mod max value. So for the moment, I want to actually show you what's happening with mod, because I know that mod is something that takes a little bit more understanding than the other mathematical operations. So we might actually just go print something out. Corrected die1 to this value. I don't need a full stop, I'll just do a new line after that. So this way, when this runs, you'll be able to see what's happening. So let's just do it like this for now. It's not going to get us the right values, but we'll actually see what mod is doing. In fact, I might just cut off the rest of the code here and just go, okay, we're just going to end the program there. So I'm going to say end the program there, but it's not a correct end of the program because it didn't reach all of this, so it's going to be return 1. So what I'm going to do is just show you what's happening when I do the mod. So compile that. Oops. Oh, I made this mistake previously. So I'm outputting a number, but I haven't given it a variable to output the number from. So die1, save that, and go again. Okay, let's run this again and see. Someone there was like, you forgot the comma. Yep, thank you. Run this and type in the value of the first die. So now I can do something like this. I just spammed the keyboard with random digits. Corrected die1 to 5. So what I've found out is if I divide this number by 6, the remainder is 5, which is pretty good. So if I run that again, different random number. If I divide this number by 6, it has come up as a 6, so it's corrected it to 0. So 6 is divided into 6,546, an exact number of times. So what you're going to see if I run this multiple times... Oops. I typed in the number before it even asked for it, but it was fine. You can see how it's changing these to values between 0 and 5. I'm typing before the scanf even appears, but it's still working. Yeah, so I'm getting a bunch of corrected values. So that's what I'm going to work with. So given those corrected values, the only issue I have is that 0 is not valid, but 1 through to 5 is valid. I should also point out that if I type in a valid... Actually, no, if I type in a valid value, it doesn't matter, because it's never going to trigger this. So what I'm getting is... I'm getting this kind of behavior where I can spam a number in and I'm getting a value that's close to, not quite yet, but close to what I want out of the die values. So the mod corrected it to that. Now at this point, die1, after this line has run, is a value 0 through to 5. Oh, there's other issues with negative numbers. I think mod of a negative, actually let's test it. Mod of a negative number I think is negative. So if I do negative something, I'm going to get a negative 4. So there are some potential issues there. There's some little things there. We're going to ignore that one for now because I don't think we have enough time to fiddle with it. But at least if we're typing in positive numbers, we're going to be able to get this correction here. So at this point in my code, die 1 is equal to 0 through to 5. Interesting things there. Someone is saying we should add 1 to the modulus. So we could do something like this. I could even put it here. Die 1 mod max value plus 1 will shift our range. So we shift it from 0 through to 5 to 1 through to 6. So this is actually one nice way we can do this by doing a minimal amount of code. This will put us in our nice range. So let's save this, compile it, and run it and see how we're going with that. So we're getting a 4 there. How do I make sure that this thing is a 0? So I could do 12. Oh, I have to run the program. I just typed 12 into my terminal. I'm too busy thinking about, like, this is what happens, right? When we're programming, we tend to be juggling abstract concepts in our head, and sometimes we forget what we're actually doing in that case. All right, so we run the program, and this time we type in a 12, which should give us a 0, which is now a 1. So we're actually getting to the point where we're only getting legal values. So if I just go through the numbers here, knowing that if I add 1 each time, it's going to go up through the sequence, I should only be getting numbers 1 through to 6. There's a 15, so that's a 4. 16 is 5. 17 becomes 6. 18 hopefully will go back down to 1. Yeah, okay. So now no matter what numbers I'm typing in, I'm getting the values 1 through to 6. So that's working pretty well. So this might be all we need. So it's this one simple line here that is saying mod and add 1 to it, and then we're correcting it like that. There's only one issue with this. So if I want to just do this in this really automatic fashion, I might actually take out this entire check to see if things were the legal values or not. And I might just say, no matter what the value is, we're going to correct it. So if I just take this line, put it here, then I have to take out these and say, I'm not going to go through any of the stuff here for dealing with detection or correction of things. I'm just going to always correct things if they're the incorrect value. Let's see what happens here. You can see I basically I've walked you into a trap here. I always used to joke with the classes about this pantomime idea. I don't know if anyone ever went to these as a kid. You go to these like little pantomime theater shows, and you go through, and like they're always really, really overt and funny about it when like the people are just walking around, and then the villain turns up behind them, and all the kids in the audience are like, he's behind you, and they turn around, and by the time they turn around, the villain has run away or something, so they never see them. So this is me doing this now, where some people are probably going to be able to see that there's an issue here in doing this. I'm going to show you what happens if I decide I don't want all this extra stuff around correcting things. I just want to silently correct stuff with this. And this is going to correct most of our values like this. So if I do this, and now I'm not stopping the program from running, I'm going to let it flow through. Let's compile this and run it. So I can type in the value of the first die. So I can do the silly things I was doing before of weird numbers like that. The second die doesn't have the checks, so it's going to have to be a legal thing. Die 1 gets converted to 1. So we can see that it's taking my incorrect value and fixing it. So I'll type in another incorrect value, and die 2 is going to have a correct value. And die 1 gets corrected to a 6 in this case, and die 2 is a 3. So this seems good, right? This seems like now no matter what I type in, it's correcting my number. So let's type in this, and let's go back to another possibility here where I go, okay, what if I did it correctly? So I've got a 5 here and a 3 here. I did this on purpose. To show you that maybe the +1's not the best solution, because I'd rolled a valid number this time and it changed it. So if I was going to do this kind of thing where I was just like, just process all the numbers with this mod thing, I don't want to add 1 to this, because what it's doing is it's actually changing the values when they're valid as well. So what I might want to do in that case is, instead of adding 1 to this, if I was just going to apply it to every number, if I don't want to bother going through the if statements and stuff like that, instead of the +1 here, I might do something else. So I can say, okay, there are potential issues with this. So I'm going to say, what are the issues? There's 2 things. So one of them is the negative numbers that we were looking at. So if after the mod, if die1 is less than 0, so this is this will usually be -5 to -1, although it's like max value, so I shouldn't use the number 5 in here. So it's negative max value minus 1. Wait. Negative max value plus 1, which is the 5. So it's either it's between negative max value plus 1 to -1. So one thing that we can do here to bring this back into the range, so if it's less than 0, what we can do is we can say die1 is now equal to die1 plus the max value. This is going to bring it back up positive. So I'll show you the example of why this is happening. If I run this again and I type in negative anything and another value for the second die, it's going to be negative something, and it's going to be between 0 and -5. And so any of those negative numbers, if we add the maximum value to them, it'll bring them back up into the range of the positive numbers. The other option if die1 is exactly 0, so that means the mod of it, so for example, if die1 was 6 and the max value is 6, it divides in exactly once and there's no remainder. This would set die1 to 0 if it started off as 6, because after we mod it, it gets divided by 6. So what we're going to do is take any time that die1 is equal to 0, so this will also work for all the negative numbers. So any negative multiple of 6 is also going to end up as a 0. We're now going to set that to a 6. Die1 is now equal to I was about to type in 6, but remember I have a value for that, which is the maximum value. So now we have a situation where we mod it, and after we mod it, we correct the negative case. I think I've got a better comment here. If die1 is negative, I guess I can say make it positive, because I know that adding the max value is definitely going to make it positive, because all of the negative mod values are going to be just a little bit lower than the maximum value. If die1 was exactly divisible by max value, set it to max value. Okay, at this point, we should get ourselves to the point where we have any possible number that we type in is going to end up being the numbers 1 through to 6. There's a good question in there. Jason said, why not multiplied by -1? We can definitely do that as well. So here, if die 1 is negative, making it positive, we don't have to just add the max value. We could do something like this. And so this is why I like coding live, because if you say something like that, I'll put it in the code because it's worth doing. Like we did the +1 before, but I wanted to also... Sometimes I like taking your offers of interesting things to do and showing how they can and can't work. But this one's one that I quite like. This one that will definitely work. If we want to make a negative number positive, we can just multiply it by -1. So if we know that the number is negative, which is like this, multiplied by -1, we should get a positive value of the same thing. And because we're not too worried about preserving values in different ways, or preserving the multiples and things, and this is like a reasonably random situation we're working in, this will totally work, right? So we just want to make it into a positive number. And we know that since it's been modded, this should be, if they're negative values, it'll be negative values in the range of -5 to 0. So if it's between -5 and 0, we flip it to positive, it goes back into the range of 0 to 5 that all our positive numbers would be in. And then we can take the zeros that we have and make them into 6s. So what we've done is, first up, the mod is going to get us the remainder of the division by the max value, which is dividing by 6, gives us numbers of 0 through to 5, then stored in die 1, negative or positive. If they're negative, we just flip them to positive, and then we take all the zeros, replace them with 6s, or whatever the maximum value of the dice is. And then what we've done now is we've silently corrected the inputs. But more interestingly than silently correct the inputs, what we have done is we've gone back to the idea of what the user was thinking of originally, which is, I want to roll dice and see if on a random chance I am higher or lower than a particular number. And what we've done is we've even solved a problem the user didn't know they had, which I have right now, where I haven't got my dice out. Sneaky. I didn't get my dice out today because I knew I was going to do this. I have made a program that kind of simulates the rolling of the dice for me, so I don't even have to pick up the dice to get this to work. So let's save this, compile it, and run it. And now I should be able to type in, only for the first die, because I haven't done the correction on the second die. I can type in basically any number here, and then let's do a valid number for the second die, and I'm going to get a value between 1 and 6 for the first die. And we've gone through and refined this, so I know that I can type in, ooh, this one's not going to work. It's got to be a number. I got a little too overzealous with my rolling my face across my keyboard there. So the negative number as well, let's type in a 5 there. And yeah, and we're getting valid values. I would have to test this with a lot of different numbers to see if this worked, but I'm pretty sure it's going to work here with a lot of different things. As long as the second one is valid, because we're not checking that one. And it's always going to be giving us a nice value between 1 and 6 for that. Someone was asking about absolute value. Absolute value is a thing, and there are ways to do absolute value in C, but we'll talk about that when we start doing things with other libraries. So I'll talk about that later. So there is a way to just get something to do absolute value in the same way that like printf and scanf are just made available for us, but I'll show those later. Okay, so I think that's where we're at now. Oh, that's good, because there's only like 3 minutes left. It's like when I look at the clock and go, oh yeah, who wrote this? They wrote this to fit into 2 hours exactly. That only works sometimes. Okay, so mod, I'm going to have to... Oh no, wait, I wasn't blocking any of the text there. So let's think about what has happened with the mod. So we can guarantee a number between 1 and 6. We're not shutting down unexpectedly, so we're we're living with the idea that the user may have had, which is that they were looking for a randomized result, so they weren't too concerned if we change the numbers that they type in. And we're getting a very dice-like result if you just spam digits now. The downside to this is we're not, now that we've made this new approach, we may be just accepting input without notifying the user that anything's wrong. However, we had code for that, so if we wanted to put that back in, we totally could. So this may change the user's expectations of what's going on in the program. So we have to think about that. For this program, this kind of works. For another program where we're testing user input, maybe, I was talking about that, like, medical diagnosis program, that would be the kind of thing where it's like, no, you would report the problem and you would not correct it because you want to be really careful with it, right? So little things like that. This is the idea that solving the problem of correcting input makes sense only specific to the particular problem you're trying to solve, right? So the context of the program counts for more than whether you're solving that one specific issue or not. So yeah, lots of different solutions. You decide between the different solutions based on why your program exists. So I like the modulus one because what it does is it brings us into this idea of pseudo randomization, dice rolling kind of stuff. But I would 100% accept an argument that the program should just reject the incorrect input and say, I cannot use this and I will not. I would 100% accept an argument for one of the earlier solutions we had, which reports the issue to the user and says, no, this is in your hands. You need to go and fix it. But I like the modulus one because it adds on that extra bit of randomness. Also allowed me to show you modulus and some other bits of code, and allowed me to push more complexity into what we were doing, because last week we used exactly the same kind of constructs. The math, the if statements, relational operators and stuff, and now I'm using the same things, but showing you how much more complex it can be, and it goes deeper, right, than this. So there's lots of little things like that. So here is the one possible finish of it. So that was the completed code if you want to look at it, but I will also be leaving the code that I've done there anyway. Yeah, so we have the complete new dice check program, dice check version 2, where we have some measures against user mistakes, and we're potentially reporting errors or able to deliver a die roll regardless of if there are errors or not. Did I have a challenge for this? Oh, I didn't. Okay, that's fine. On Friday, I will do something that has a challenge. But yeah, we should wrap it up there because we're at 1 p.m. now. So today we did a quick recap of all the program we've done so far, but we also looked at problem solving. So what I want the message from today to kind of be is that problem solving is always based on the situation that the problem exists in, not necessarily whether the code is working or not. And there are many, many different ways that we can solve problems, and it's all about, continually modifying and remodifying your code and stuff like that, and testing each of these solutions against your expectations of how the original goal should be achieved. And so hopefully this helps and gets you into these ideas of what's going on. Someone's like, we need a challenge. Well, I'll give you a challenge on Friday. I know that there's something that we're doing on Friday, which is more advanced than what we're doing here. Actually, it's more and less advanced. It's easier to think about than mod. Mod kind of like rewires your brain in strange ways, but on Friday we're doing something which we're doing looping code on Friday, and that is something that's easier to think about. Anyway, I'll end the lecture there. I've now gone overtime after I was on time, and so I'll go into my be right back screen, and I'll come back in a second, and I will answer anyone's questions they have about things. So I'll come and take part in chat and answer questions afterwards. So that's the end of the official lecture. Thank you very much, everyone. Alrighty, I'm back. Stuart, I think YouTube is blocking you because of the combination of letters that you're using, so I just let one of the messages through. Okay, so people simping for chicken. She's still there. Hang on. Let me just... Yeah. There you go. You can see her. She's just curled up. It's nap time. Alright. So, questions. And I saw multiple questions there that looked nearly the same, which were, can we explain modulus? And yes, we can definitely explain modulus. So, the way that mod works is if we have a division of numbers. So let's say, for example, we'll keep it within the example that we're using here, which is dividing something on mod 6. So if I have a number like, that's not even remotely a number. So let's have the number 13 mod 6. So you've got me in maths mode here, so I'm using paint. This should be for in person. We're like, all right, I'm gonna go onto the chalkboard or the whiteboard and use this. So 13 mod 6 is, if we divide 13 by 6, what is the remainder? So 6 times 2 is equal to 12, and the difference between 12 and 13 is 1. So the mod of the mod of 13 by 6 is 1. So what this is saying is, if we were to divide this 13 by 6, is there a remainder, and how much is the remainder? So another like example of something that does work exactly is something like 18 mod 6. You can tell I'm writing text with a mouse right now. This is equal to 0 because 6 goes into 18 an exact number of times. So this is us getting to the idea that a lot of the time in programming, when we're using integers, we're going to be doing integer mathematics, and integer mathematics does not have space for fractions, because integers are only whole numbers. And this, I think, is a byproduct of the fact that the computer is only storing zeros and ones. So because it's only storing zeros and ones, the concept of a fraction doesn't necessarily exist at the most fundamental level. At the most fundamental level, the idea of quantities, where the smallest difference between numbers is 1, like 1 or 0, right? That's the only way that these things can work. So it's interesting to think about it that way. So if we do another number, let's do smaller numbers so that I don't have to work out the division in my head. So if we did a number like just 8 mod 6, so 6 goes into 8 once and the remainder is 2, so 8 mod 6 is equal to 2. Note that no matter what numbers I put in here, so the 13, the 18, the 8, I could put something in the hundreds or the thousands, the remainder in a division is always in the range of 0 to 1 less than this number. So 0 means the number fits in an exact number of times, and then the 1 through to 5 are the possible remainders if the 6 didn't fit into that number an exact number of times. So hopefully that's helping people with like the mathematical idea of what mod is. So basically, like, yeah, I'm going to say x. Yeah, we're getting real mathematical here. X mod 6 is always going to be 0 through to 5. Oops. Let me just let you see that. So I don't know if my mathematical notation is correct there, but I know that there's another way to write in maths the range 0 through to 5, but you get what I mean. Yeah. Oh, okay. So people were asking about negatives. So negative mod would be a kind of a negative remainder. So if I did say negative 15 mod 6, I would know that if I divided 6 into this twice, that would take 12 off it. So this should be a -3. So if I put 2 6s into the -15, you could take 12 away, or I mean, like, you could go back towards 0 by 12 in a sense, so you'd get a -3. So it's nearly like the mod, when it's negative, is the same thing in terms of the digit, but then you just put the negative in front of it, as far as I know. I might have to actually, like, run that and see, but I'm pretty sure it works like that. Ricardo's saying C gives -9 when you do -5 mod 6. Huh. And Python is doing positive mods. Joanna, I think, is maybe running it right now, and she's getting a -5, so hopefully it's -5. My whole idea of maths and my trust in programming is going to get blown out the window if that thing wasn't even a negative value between 0 and 5. Because you shouldn't be able to get a remainder that's higher than the dividing number. But I would have to do some testing and look up the actual specifications of these things if it was doing something that I wasn't expecting. And Feyumar is saying, why is 5 mod 6 5? So if you think about, like, 5 mod 6, 6 divides into 5. Let's write this up. 5 mod 6. So 6 divides into 5 exactly 0 times, right? So if it goes into 5 exactly 0 times, the remainder, the leftover, is 5. So this is when you're dividing something by a number that's bigger than it, it will never divide into it. And so that number itself becomes the remainder. And Hamish is saying, Python is saying -13 mod 6 is 5. I have no idea what's going on there, Hamish. It might be that the way Python is doing it is the same way that I was doing it when I wanted to flip those positives and negatives here. Instead of flipping them by -1, I was adding to them until they became positive. So if you consider that if you have -1 and you keep adding 6 to it until it's positive, it'll end up being 5. So -13, if you add 6 to it, becomes -7, and if you add 6 to it again, becomes -1. If you add 6 to it again, it becomes 5. So Python may be doing it that way. So taking these sequences of 6 numbers at each point and saying which one of those sequences of 6 I am. Possibly. I'm not sure exactly. Okay, so what we're seeing is that mod is potentially a very weird space to be in. And I think what this means is that anytime we use mod, we want to be reasonably sure about what we're doing with the negatives and positives. We're getting away with it in this particular example because it's a number randomizer. I'm going to say randomizer. It's not actually random, but it is kind of a randomizer. So we're okay with that because of that. And Waleed is saying that C's implementation is slightly different to other programs' implementation. I think the reason behind this is that mod of a negative value is not necessarily defined mathematically. So everyone's just sort of making up something that does something with it otherwise. Because division of a negative number sort of works. I don't know. So I'm not actually too deep on my maths to be able to tell whether that's theoretically possible even, because division is about quantities and a negative number is not really a quantity, but you know, so there's a lot of like possible weirdness going on there. Yeah. So Brendan's helping out there. I think Brendan's response to Fei Wei there was like a good thing. So you can see it as 5 equals 0 times 6 plus 5. Yeah, that's how you see the remainder. Waleed's saying there's a post on Stack Overflow somewhere that says stuff about mods and their weirdness. So it's going to be different. Hamish is saying Python is written with C. It can be written with C, but that doesn't mean it's implementing the same things as C. So they may have decided when they wrote Python that they wanted mod to work in a particular way, whereas the default C mod is slightly different. So it might be that Python kind of turns into some of the machine code that C does, but that doesn't mean the same symbol is going to do the same thing mathematically, which I think we've seen. If you've done Python before, you'll see that C and Python don't work the same way. Not exactly. P10 is saying don't use negative mods unless you're trying to break something. Wait, Waleed's saying that 1081 has defined negative mods, but the C doesn't follow the proper mathematical definition of mods. I think this is quite funny. I think Python might be the correct mathematical definition of mods, but I end up using the C definition because I've spent so much time in C that I think that that is correct. And so what we might be seeing is that C's % symbol is very close to the mathematical idea of modulus, but may not be exact and may not be doing things the exact way that that would happen in proper proven mathematics. I think 1081 is discrete maths. Yeah. All right. Does anyone have any other questions about the code? I think we've talked about mod a lot, and I think what we found out is that mod is a bit complicated, and we want to be a little bit careful around it. So let's see if there's any other questions about the code that we wrote. If anyone wants me to clarify the code, I'm going to actually do some clarification here as well by putting some comments in. Just so that when people download this, it runs correctly and they know which sections do what. Because I've just commented out this whole section here, and it's in weird chunks, so I'm going to need to explain what's going on there. Looks like Waleed's going for a nap at 7 a.m. nap. Oh, P10's asking a question. Why did we do return 1? So there's a difference between the return 0 and the return 1. So return 0 is like saying, you can actually leave this off, and the program will return 0. So it's an old school thing that we don't actually use that much anymore, but it's worth kind of knowing in case it gets used. Return 0 says that the program ran correctly, and return anything other than 0 is saying there's an error in the program, and here is a code to talk about what the errors are. So I use return 1 here just because when I was doing the mod, I just wanted to show the mod value and what we were doing with it. So it doesn't actually need to be there. And what I might do before I finish saving this out for everyone is I'll change this stuff so that it actually makes sense. Because we could still do it inside this if statement with the reporting and stuff like that, and I could put the mod in here again. So I might move this stuff around before I save it and send everyone. Oh, Caleb's asking, when we learn loops, would that be the preferred method of resolving user input error? Quite possibly. So there was one of the options that I put there, which is like ask the user to go again. And that definitely would work with looping, which is actually going to be this Friday's lecture. But in the looping this Friday, I'm not going to use this code again. I'm going to start a new program that does more interesting looping than just asking someone to input again. But yes, looping allows us to run the same code multiple times, and we'll get into that. We'll get into that on Friday. So I'll talk all about that to everyone on Friday rather than just whoever's stayed back for questions. Oh, P10 was asking, why did we comment out return 1? I commented out this entire section because it was code I wasn't using. So at the moment, my program's really not very neat and very hard to understand. So what I might do is have this mod section here and have this other section which is doing the checking and the reporting and stuff like that, which doesn't include the modulus because I've moved the modulus out. And then we don't have the return 1 because we didn't actually want it to end there. So this section is something you could turn on if you commented out this section and used this section instead. You would use the clamping and the reporting instead. And if you want to, you could actually have some of this stuff on, some of this stuff off, put some in different places, and have your program run in different ways. As we kind of are learning with C, all the different chunks of C work on their own in a sense, and we move them around, do them in different orders, different things are going to happen. And it's a matter of sort of experimenting, writing lots of different programs, and you sort of learn how to put all these pieces together. So it's like a jigsaw where every piece fits with every other piece. And so it's up to you to decide what it looks like in the end, I guess. Ricardo's asking what my LeetCode global rank is. I'm not on LeetCode. It's actually been many, many years since I've worked as a professional programmer as such. Because even the last time I worked as a computer scientist as such, I was one of those people who I was talking about earlier, who I would spend like 2 months on a whiteboard and then 1 day coding. And that was considered good work, because it was hard. I was working on what we would consider to be like things that are really hard to think about. But you would write you'd write a few hundred lines of code, but the work was done in trying to decide what the code was rather than the difficulty of getting the code to actually look correct in a sense. So I think that I probably wouldn't be that high on LeetCode if I hopped in on it. It's probably better that I don't, because I'll lose respect from my students if everyone's higher in LeetCode than I am. Henry's asking what happens if we do return 1. So, return -1. If you do return -1, all it will do is end the program wherever you put the return statement. So wherever you put the return statement, every line after it won't run. So if I do something like this, this program will appear to not have done anything. All it will have done is created 2 variables, and then the program will end there. If I'm piping that program into another program, which we're not even looking at in 1511, we're just doing one program at a time. But if I was running this kind of within another program in a sense, that other program would know that it got a -1 from this one. So it would say, if we got a -1 from that one, then it's trying to tell us something. It's trying to tell us that something didn't work properly. And then maybe I would have to have a communication with the programmer who's writing the other program to tell them what to do when a -1 happens or a 1 happens. Or for example, like a 404 happens. This is a web error, so it's a different thing, but this might remind you of things you may have seen before online. You can get 404 errors when a web page doesn't exist, that kind of thing. So yeah, any number other than 0 is considered a non-standard finish of the program. I think that's what Kelly's asking there. Yeah, you're asking, could we do return 1 or return 2? Yeah, any of those things will return the program. The convention that we use for this kind of thing is to say that return 0 is everything working, and return something else is stuff not necessarily working. And then what those other numbers are is up to you. So you could have a document that says, here are all the possible return values of my program, and this is what they mean. This is why it's old school, returning the number, because if you need to explain it outside of the code, chances are it's going to get lost and no one's going to know. So they still exist, and you still could use them, but it's not necessarily something that we would definitely do anymore. So it is a little bit legacy, which is why later on in the course you will see me sometimes write programs where there's no return 0 even. I'm just like, nah, if it ends, it ends. It's fine. No one's looking at these return codes anyway. Caleb's asking if there are standards for those return codes or it's a per project thing. It's usually a per project thing, but it also depends on which kind of error codes. So online, on web pages, they're very, very well defined. So there is like an ISO standard for them. It says these kinds of codes, if you give these kinds of codes, it means this. 404 means the web page wasn't found. 400, I think, means that you don't have the security permissions to view the particular thing. There's other numbers. I think there's an 80 for something, or 80 is the port number. There's all I don't memorize those, but yeah, this is like Hamish is saying 400's a bad request. So there's some reason why. That's also a really bad error message. Bad request. Like, what does that even mean? Right? It's like I always find like the less words you put in the error message, sometimes the harder it is for anyone to actually figure out what to do with it afterwards. So yeah, lots of those things. They're things that are well known and well defined, and you get to the point where, like in chat here right now, people saying 401 unauthorized, 400 bad requests, 500 internal server error and stuff. So you can see people know these because they've seen them enough. I'm assuming all these people have tried to do some web development and have had these errors thrown back at them when their web pages didn't work. Yeah. So yeah, that kind of thing is well known. But if you're writing a program from scratch, 403 was one I was thinking of, forbidden. Yeah. But yeah, if you're writing a program from scratch, then the error codes are going to be whatever you decide they are. In general, though, it's not something that we're going to be teaching or using that much in COMP1511. We're hardly going to be doing it at all. Most of the time what we're going to do is we're going to say these programs are going to make it to the end. And if they're not going to make it to the end, if we want them not to make it to the end, then we could just do it with an if-else statement and saying they always make it to the end. But I could say this entire body of working with adding the variables up could be in an else statement or an if statement instead. When we get deeper, we're going to show you other ways of doing this with these things called functions, but not going to talk about that now. We'll do it later. Okay, I'm going to wrap it up there. Thank you, everyone. I will do a little bit with this code, although I think I've done everything with this code now to make it neat enough that you could just swap the comments here and run either one of these and you get different solutions and it would work. Yeah. So I think I'll leave it in its current state here. All right. Thanks all. See you on Friday. We're going to add a new coding construct on Friday, the ability to run code multiple times. So that'll be interesting. And we'll have a new example then as well. All right. See you later.